Well, welcome to part 2 of our engineering portfolio project. In part 1, we focused on the linear equations and the quadratic equations, and specifically in the world of engineering, we focused on both circuits, we focused on velocity, and then we focused on springs. Okay, so what we're going to do here in the second portion of this is we're introducing a new thing called, or it might be new depending on whether how far y'all got in your high school or your last math class, and depending on what you took, is we're looking into a system of equations. A system being, how can you solve more than one equation at a time? How can you solve 2 equations, 3 equations, 4 equations? The more equations you have, the harder it gets, obviously. But we're going to focus on pretty much just solving a system of 2 equations, which means we're going to have 2 equations and 2 variables, and we want to solve them at the exact same time. And in a nutshell, when you're solving more than one equation at a time, what you're really looking for is, if I was going to graph everything, you're looking for those intersection points. In a nutshell, that's basically what we're finding. But okay, here in this first concept, we're visiting with going back to the circuits. Okay, and the first thing I noticed is that during the scanning process, something didn't show up. If y'all could write up here on your graph or on your chart, if you can say that you got 2 little resistors up here that don't have anything labeled there. This first one is 6 ohms, and the second one is 8 ohms. For some reason, it did not pick up during the scanning process, but just get those in there and then we can start the problem. Okay, so what's happening is you basically have a 2-loop circuit, and we're going to use our basic equations that we used back in the first part of the portfolio, which is obviously is Kirchhoff's law. Kirchhoff's law says that the sum of the voltage rises equals the sum of the voltage drops, and then we also have Ohm's law right there, where voltage is equal to current times resistance. Okay, so let's focus on these 2 equations that are given right here. Where did they come up with? Okay, well, they're based on Kirchhoff's law, and that says the sum of the voltage rises, and the rises are your sources. So if you look up on the graph, the sources are 6 volts and 9 volts. That's why it's 6 and 9 right here on the right. So everything on the left is representing the sum of the voltage drops, because you basically, is when you make one full loop on that left side, or you make one full loop on that right side, as I come around, or as I go around this direction, always going from positive to negative on my current, that I'm actually crossing 2 things, a resistor up there and a resistor in the middle. Resistor up top, and again a resistor in the middle. Okay, so what these 2 represent, let's look at this main first equation. Where does the 10I come from? Okay, well, 10I1, because what this is telling us is here in the first loop, in the I1 loop, that goes from here all the way around to there, look what I cross, 6 and 4. Both of these are in this I1 loop. Okay, so that's why the 10 and 6 plus 4 is 10. Now why the 4 is repeated, because it's saying that when I go around this loop, the part that I touch of the I2 loop is the 4 ohms. So that's why the 4 right there. So 10 is saying, in other words, that 4 almost gets doubled up, yes. You're getting 6 plus 4 when I go through the I1 loop, and then of this whole loop, as I go around this circuit, what I'm touching of the I2 loop is the 4 ohms. Okay, so let's go to the right one, or the second equation. Of the 9-volt circuit, as I go around this loop in the I2 circuit, 8 plus 4 is 12. So of the I2 circuit, it's 12. And then as I go through this loop, what I touch from the I1 circuit is the 4. So again, 4 gets repeated in both cases. And that's where that whole these 2 equations are built off, is the fact of going one full loop in your circuit, plus what you touch of the other circuit, and then one full loop of the second circuit plus what you touched of the first circuits. Okay? And taking this now to math. That was the engineering portion. The rest of this is more the math portion. Okay? What you see above are these 2 equations right here. And it's what we say is it's a system, it's a 2x2 system. It's 2 equations and 2 variables. 2 equations, obviously, and the 2 variables being I1 and I2, current 1 and current 2. Okay? And we want to find I1 and I2. And what we're going to do is find it 2 different ways. One through matrix algebra and another one through Cramer's rule. And I'm going to talk to you about both of these as we go throughout it. Well, the whole goal with the matrix, the key is taking your system of equations and only focusing on the numerical coefficients of it. So the numbers in front of the variables. Okay? Matrix, we call matrix A the coefficient matrix, because Where it pulls off are just the numbers, the 10, 4, 4, and 12, as y'all can all see right there. Okay. Here in column 1 of it, it represents all those numbers that came off of the I1 variable. Here in column 2 represents all the numbers that came off the I2 variable. If there was a third variable, then there would be a third column, but each column represents the coefficients coming off of each variable. If they were out of order, the variables were up in the equation, you have to rearrange them, make sure they're in the correct order, and then you can make a coefficient matrix. Okay. X represents basically the matrix of your variables. The two variables there were I1 and I2. If the variables happen to be X and Y, then what you would see here is X's and Y's. Okay. And the third matrix that we're going to use to help solve this is is basically what I call the equal matrix. It's what's on the right side. So one matrix represents just the numerical coefficients, one matrix represents the actual variables, and then one matrix represents what the whole system equals to. Okay, so from here we're going to take those three matrices, or the three individual ones, A, X, and B, and here's some very important information. For any system, your coefficient matrix times the variable matrix is going to equal the 6 and the 9, what it's going to result to. So it's like basically here on the left side is those two combined together would be your main equations that we just developed, and then equals the 6 and the 9. Okay, so if you want to solve for this, if you want to get X by itself, we need to move the A off the left and put it on the right. Well, if you move it off the left and put it on the right, you have to write it in the form of inverse. Okay, so X is equal to the A inverse times your solutions. Okay, so for a 2 by 2 system, if A, matrix A, has the numbers, let's say A, B, C, and D, just like this, the quick, easiest way to get the inverse of it is look at this. What you're going to do is you swap the first and fourth items around. So that's what now you see D and A. C and B say that we're exactly where they are. All you do is change their signs. They go from positive to negative or negative to positive. So what it is, you switch the signs. So swap the first and fourth, and then switch the signs on the second and third entries in your matrix. Okay? And then after you do all that, you have to multiply this matrix by 1 over, and it looks right here like I'm saying the absolute value of A, but I'm not. That symbol, what it means is finding the determinant of A. So this right here, this whole absolute value of A, is actually the determinant of A. And how you find it, you just use this equation right here. It's AD minus BC. So first times fourth minus second times third. Okay? So let's go about finding our answers here. I kind of got all that kind of set up for you. Just a little bit. Well, writing out some stuff that I know that AX is going to equal B. Okay, so A is that coefficient matrix, which is 10, 4, 4, and 12. Our X is our matrix of variables, which is I1 and I2. And then B represents that matrix of what they equal to, which is 6, 0, and 9. Okay, so that's AX equals B. So from there, in order to actually solve, remember we need to convert this over to X equals A inverse times B. Okay, so X equals, so I1, over I2, not really over, but it's not really a fraction, they're kind of just entries in here. But you have I1 and I2 is equal to A inverse times B, and B is 6, 9. Okay, so all I have to do is now go about finding A inverse. Okay, let's do this. So A inverse is going to be 1 over the determinant of A times this new matrix, where I swap the first and fourth entry, and then I switch the signs on the second and third. Okay, so in terms of us, then A inverse, and then obviously the determinant is AD minus BC. Okay, so it's 1 over A times D, so 10 times 12 minus, and B times C, so 4 times 4. I'm going to write all this out for you guys, kind of step by step. And then the matrix, when I swap the variables or the numbers and everything around, so 12 now becomes the top right, 10 becomes, the top left, 10 becomes the bottom right, and I'm going to switch my signs so they become both -4 and -4. Okay, so let's keep on going. So A inverse is going to be 1 over 10 times 12, so 120 minus 16 will be 104. 1 over 104 times then the 12, -4, -4, and 10. Okay, so what that means is to finish out finding A inverse, I want to go up there into that matrix and multiply everything in that matrix, or if you want to think about it, divide everything in that matrix by 104. So when I do that, 12 over 104, let me give myself just a little bit more room here. 12 over 104 reduces, kind of did some math for you guys just a little bit, to 3 over 26. Okay, -4 over 104 is -1/26. And then a -1/26 there again, and then 5 over 52. Okay, so that's what our inverse matrix is going to equal. So we just kind of plug that right back up into there, and then I'll be able to keep solving some more. Okay, so let's come down. I1 and I2 is going to equal my inverse matrix. Just rewriting again everything, times my solution matrix, 6 and 9. Okay, so from here we get the wonderful stuff of just being able to pull our calculators out and letting our calculators tell us the answer. Okay, so what I would do is, in your calculator there's this button called your matrix button. It's right behind, just on the left side, if you have a TI-83 or a TI-84 plus. I specifically use the TI-84, and the button you're looking for is over on the left side. It's the fourth one down, and it's going to be, you're going to have to hit the second button and hit matrix. And what you do is you just enter in, let's say call this one matrix A, call this one matrix B, and then in your home screen all you have to tell it to do is go A times B, and it'll give you your answer. Okay, so if nothing else, if you guys want to take 2 seconds, I'm going to let you guys do that on your own, of figuring out how to really use your calculator. You can obviously go onto any TI's website, or if you happen to have a Casio, go on Casio's website. If you want to look at your manual, you can look at your manual. If you want to take this to the math lab, I mean, really, it's going to take all of 2 seconds. Just let somebody else show you real quick, okay? But when you do plug this in, what's going to come out, your calculator is going to spit out a matrix. It's going to be a 1-column matrix, say something like 0.3462, and then 0.6346. And that's what's going to come out. And how you match it up is, obviously the first one represents I1, and then the second one represents I2. So that's a way on how to find I1 and I2 using specifically the matrix method. Okay, so it's all based on the fact of kind of reviewing a little bit, is you want to find your coefficient matrix, and then from there you want to find both. You want to find the inverse by swapping the terms around, switching some signs, and then finding your determinant, and then from there just plug in your calculator. Alright, so let me erase some of this up, and let's go about finding this exact same stuff, see if we get the same answer using Cramer's rule.